Hello everyone, welcome back to another mini concept, this time about reversible reactions and equilibrium. So a bit of an intro to equilibrium. As we all know, it's a fundamental state of nature to want equilibrium. In physics, we wanna achieve a net force of 0. In biology, we wanna achieve homeostasis, the state where our bodies are able to regulate itself naturally. Now, in chemistry, we have two types. We have static and dynamic equilibrium. So from the words itself, static means it's not moving, and dynamic means that there is something moving. If we take it in the context of the types of reactions, we can see why dynamic equilibrium happens in reversible reactions, while static equilibrium occurs in irreversible. Let's expound on that a little bit. So let's say that we have A and B as our reactants, and they're converted into C. Now, in irreversible reactions, A and B will completely turn into C, right? And in this case, let's say that these are completely used up. This will have 0 moles after everything, and C will have everything else, everything that A and B was. So the initial of A plus B. Now, this is what we call static equilibrium, because nothing is going to be moving back and forth, nothing can further turn into C, and nothing is left over. So everything on the left side turned into the product. Now, how about if we have this larger reaction? Let's just expand it a little bit so that it's a bit easier. Let's say that this is a reversible reaction. Now, a reversible reaction is on the contrary. It can turn forward and it can turn backward, as indicated by the back and forth half arrows. Now, when it can go back and forth, dynamic equilibrium is achieved only when the rate of both the back and forth are equal. So we can say that like the rate is equal. Rate of the back is equal to the rate of the forward reaction. And this also happens when we have the concentrations of the left and right side equal. Now, what does that mean? So let's say that A and B, A plus B, will react to form C and D. Now, there will be a point where A and B will no longer turn into C and D, and C and D will no longer go back to convert into A and B. So, where can we see this? So, in acids and bases, they normally go back and forth. They normally dissociate and they normally go back to form their parent ions, especially in solutions. Sometimes they tend to go back and forth depending on the weakness of the base or the strength of the base and acid. Now, once there's a point where they no longer go back and forth, that is dynamic equilibrium, because neither side will be wanting to turn into the other. We'll expand on that in a more numerical way in the next video about equilibrium constants. So now that we understand the basics of what dynamic equilibrium is, wait, hold on, let's just write this. The concentration of the reactants and the concentration of products is constant. There. Now that we know the gist of what these two are, let's give some examples. So an example of an irreversible reaction is combustion. In our cars, we combust the gas and we turn it into carbon dioxide and etc., right? So we convert it essentially. So once we burn it and make it combust, we can't turn it back to its parent state, which is fuel or diesel, gas, whatever you use in your car. You can't turn it back to whatever it was. So that's an irreversible reaction. Now, in reversible reactions, like I mentioned earlier, we have, for example, acids and bases, or more commonly, phase change. It can be phase change because, let's say, for example, that we have a jar of water and then we apply heat to the jar of water. It can go back and forth from being vapor and liquid depending on how we add heat, and at a certain point it will be equal because there's going to be dynamic equilibrium because it's a reversible reaction. So I hope that is helpful to you guys to understand what equilibrium is in the context of reversible reactions and irreversible reactions, because in the next video we're going to be going more about reversible reactions as we tackle equilibrium constants. So thank you everyone, and goodbye.